My name is Chris Sewell and I work in the Theos group of Nicola Marzari in EPFL Switzerland. Today I'd like to tell you about the work we've been doing to develop common workflows for computing materials properties using the AiiDA platform. So in this talk I'll just take you through what the AiiDA platform is, how we use it to create workflows, and how we built on this to create common interfaces for multiple simulation codes. And finally, how we made these workflows both easy to use for non-experts, but also fully configurable for advanced users. So what is the problem we're trying to address here? Well, I'm sure you all know that the prediction of materials properties, in particular using density functional theory, has really grown in interest over the years. And this is in part due to the rapid increase in the number and size of computations that we can now run, but also alongside this, the steady increase in the diversity and robustness of available simulation packages and theoretical methods, which has really allowed the scientists the possibility to select the optimal capabilities for their research. With all this added power, we can now think to apply large-scale exascale screening studies for the discovery of materials. So high throughput computing, though, comes with its own set of challenges. The first one is workflow automation. We need to have the tools to be able to define and manage complex workflows, and we'd also like these workflows to deal with simulation failures for known failure modes. At the same time, you don't just need the workflows, but you also need to have an engine where the workflows can run in a robust way. And when you're doing this, you need to manage all the data that's produced, not only to store it in an efficient way, but also make it easily explorable. And an important point for us also is the one of reproducibility, that you store enough information in order to be able to fully reproduce any computational workflow. And this also really feeds into the fair access to data and computing that was mentioned in the keynote speech at the start of the day. So in order to address these challenges, we created the AiiDA platform, which is an open source Python package to compose and run workflows. And it provides a number of features, including a scalable workflow engine, automated tracking and storage of data, built-in support for interfacing with compute resources. So it will automate the submission and retrieval of simulations on any HPC or supercomputer facility. And it also has a flexible plugin system for extending the core functionality of AiiDA. My colleagues actually already presented AiiDA here back in 2020, so I won't go into too much detail about the full technicalities of it. But I will recap a core design idea of AiiDA, which is to represent the full history of any piece of data created, known as its provenance. So very simply, you start from the concept that any calculation connects a number of inputs to a number of outputs. And now, if you imagine that any data can also be the input of another calculation, you end up with a directed acyclic graph that can describe multiple steps of a complex workflow. AiiDA itself is not actually specific to material science, but if we take the example of a materials properties workflow, you could imagine taking some initial atomic structure and running it through a number of computational steps to compute a certain property. And this graph gives you the basic concept, but when you look at real provenance graphs, as created by AiiDA, they can look something like this on the right. So they're very easily quite complex, not because we represent things in an overly complex way, but that's just really what we do as material scientists. When you run, say, a molecular dynamics simulation, you may have to do a lot of runs, some pre-processing to prepare the structure, maybe a mix of DFT with some classical methods and so on. And so the graph, which represents the inputs and the outputs of every calculation, becomes very quickly very complex. At the bottom right here is a graphical representation of an actual database with calculations of basic electronic properties of around 500 materials. So not actually a particularly high throughput study, yet the amount of connections you have in the database is already so large that it's essentially impossible to reconstruct later. Even the most diligent of us will not really be able to reproduce in detail what has been done and describe it in a paper. You need to have a tool like AiiDA that tracks this provenance while the simulation is run and stores all the metadata for the calculations. As I mentioned, AiiDA has a pluggable framework, and by that I mean that you can create your own Python package to create a plugin and use the Python entry point system to declare new components such as data types, calculations, and workflows. And these can be loaded by AiiDA in Python run scripts to compose and submit your calculations in a very standardized and modular way. To give you an idea of what this looks like to implement, I have, for example, a Quantum Espresso code plugin, which tells AiiDA how to generate the input files, how to call the code, how to pass its output files. A structural relaxation workflow, which is on the left, then calls this plugin code, plus handles automatic restarts on failures, like if you reach the wall time on your HPC. Then this can feed into, in the center, a more complex workflow, like a computing a band structure, which then we load on the right via entry point into the scripts and run with AiiDA. When we run this script, you create your provenance graph and you make out some final results. So to help make these plugins discoverable, we also created the AiiDA plugin registry, where anybody who has been developing a plugin can add it for users to find. We now have this community of many plugin package developers providing different types of plugins with lots of workflows focused on computing different materials properties across the different material simulation codes. But having a code plugin and standardized data formats is only the first step. What we really want to achieve is to have some kind of turnkey solutions, turnkey workflows. And here I've made the analogy with cars. If you have a car and you want to drive it to work, or you want to drop your kids off at school, etc., you don't want to be the expert of an engine to know which pipes to connect with what. You want to be able to get in, turn the key, and just go. So what we want then is to have something where I press a button and it runs a simulation as simply as possible. Not only runs it, but also that it's reliable and robust. And we don't want our car's engine to break, and in the same way, we don't want the calculations to fail. So to drive a car, you still need a driver's license, and similarly, we still expect users running simulations to have some basic knowledge of what our crystal structure is, what properties are being computing, and what the limitations of the methods we are using. But then, like changing a car, you don't want to have to learn how to run a simulation again when switching between simulation codes. Because, say, you have a license for that code, or it has capabilities that you need above what you were using before. At the end of last year, then, we published the first Common Workflows paper, which is an initial implementation of our solution to compute materials properties using 11 different quantum DFT engines. An effort which started with a few codes, but quickly was open to many more contributions. And you see here all the simulation codes that are involved, and everything we did is fully open, both in terms of the data generated, but also the codes and the workflows to create that data. The key idea is, let's say I want to compute a material property, then now it's possible just to run this command line at the top. I ask the AiiDA Common Workflow tool to launch, say, an equation of state computation with siesta code on an aluminium crystal structure. Then we have this protocol to dictate the choice of numerical parameters, which hopefully, for the precise protocol, gives some kind of relatively high level of accuracy. An important outcome of this is now I can just change the strings for any of the other 11 codes or another crystal structure and just press the button again, and the result we get will be something like you see on the right, which is hopefully where hopefully everything agrees. Note that I don't have to tell the tool any exact parameters to use. So in order to determine these parameters, as opposed to defining all possible parameters for any code, we went for a practical approach. We simply define a set of protocol strings, fast, moderate, and precise, and that every code will have to implement. And it's then up to the simulation code specific expert to choose such parameters, with the requirement, at least for the precise protocol, that the results should match within a certain level of precision. The protocol is just a human readable name. And then in our supplementary information in the published paper, we tried to give a concrete description to the experts of what is required. And since this is all run in AiiDA, you can then go back and check exactly what all these numerical parameters are for each simulation. And I can tell you that at the start of this, many of the output plots that we got, many of the properties that we computed didn't align at all. They were all over the place. But working with these code experts by iterative discussion, we managed to align them, essentially find robust choices of initial parameters. This, however, is not enough because it's highly likely, if you've ever run a DFT code for almost any of these simulation codes, there'll be a number of issues you might encounter. Some are relatively basic, like the wall time of your supercomputer was reached, so you have to restart from the last relaxation point. But there are a number of other things, like a self-consistent calculation is not converged, or the diagonalization method crashes, etc. And for each of them, an experienced researcher for that code often knows how to fix the problem, how to change the parameters in most cases. And this can be automated. And I stress that this fixing of errors is very code specific. But AiiDA makes it quite easy to define these error handlers, which we cite error by error, how to fix it, what inputs to change in order to try to achieve this successful result. And then implementing it is down to the 11 or more plugin developers. So putting together the automatic parameters and robustness is a good start, but still we can do better. Because every code will have different ways to specify any inputs, different output formats, different routes through which the workflow goes. And this is not easy for researcher scientists to switch between. So just to give you an example here, there's some real graphs using the Siesta and Quantum Espresso codes for the atomic relaxation workflows on the left, and then the right when these workflows to use as a component of a larger equation of state workflow. And you can see graphically that even the topology of these graphs is different. And so what we did in the next step is to define a common format for the inputs and the outputs. We define a very small set of mandatory inputs for a crystal structure relaxation, which was the first common workflow interface we defined. We just need to define the crystal structure itself, of course, a protocol string, the type of relaxation you want to do, so whether you want to fix the atoms or the cell parameters, etc. And finally, you define the engine, so which simulation code you want to use, on which computer, the local computer or your HPC you want to run, with what CPU resources and wall time, etc. Then we also standardize a set of optional but standard metadata inputs. So things like thresholds for forces and stresses, the electronic type, if you know it's an insulator or metal, the spin polarization, if you want to use magnetic systems, and in case you want to study an anti-ferromagnetic material, you can already specify in a common way for all these codes how to specify the initial magnetization per site. Then at the same time, we also standardize, of course, the outputs, because once you run it, you want to have an easy way to be able to understand what's been run and link these up into more complex workflows. So things like forces, stresses, total energy, relaxed structure at the end, and the total magnetization are all standardized. Then a final goal, as I mentioned, was to make it both easy for a non-expert to run, but also customizable for expert users. And the practical solution we come up with in the design implementation is splitting the common workflows into two. So on the outside, we have the common inputs at the top and the common outputs at the bottom. Then the core workflow, what we actually call work chains in AiiDA, is going to be code specific. So this could be maybe a siesta atomic relaxation. And the only requirement it has is to produce the output in the common format. But the input can be anything it wants. It can be very specific and very detailed for that code. Then at the same time, the second requirement we have is that any of these workflows comes together with an input generator. And this will take common inputs and then will generate any output needed to be directly passed through to the workflow. So this kind of two-level design achieves what we call optional transparency. A non-expert user would just use the two as a black box, and we can just set the common inputs, take whatever their input generator generates, pass it to the relax work chain, and then look at the common outputs. But an expert user could then go in, look at the intermediate output, and change them at will with anything they want. So how does this look in the code? Well, you can see that there's in the Python, you just load the specific workflow implementation, grabbing here the siesta common workflow. You import the structure in a way which is the same for all codes. That can be from a file or from a database, etc. And then you can specify again in a common format which code you want to run, how many nodes and what is the workflow time. And then you just call this input generator that I was mentioning, which takes the outputs and generates what we call a builder. Now, if you're a non-expert, you just submit it and it runs, and AiiDA will take care of all of the submitting to the HPC, running it, getting back the results, running the next calculation, etc. But if you're an expert, you can go here and you can modify some of the lines in the input builder to modify the computation to how you want it. So the question might be is, does it work? Well, is it possible to really make it for 11 different codes? And the answer I'd give is yes. I want to stress it, in the first paper, the goal was not about demonstrating numerical accuracy, but more to demonstrate that the concept works and is possible. And I'll mention next, we're now in the process for a more stringent set of validations using a range of oxides. But here we just picked one per each of these categories. And then the results you get for all the different codes, as you see, they're not perfect, but you already get a very good agreement. So now we have this initial working implementation. I just want to briefly mention our future plans for the second phase of this collaboration. We're trying to achieve a number of different goals. The first is adding new codes, and naturally, if you're interested in adding one, then please get in touch. We're extending and increasing the number of common workflow interfaces and implementing them for different codes. So this is design that we have to go through, defining the inputs and the outputs, and going through this whole design implementation. Then the other thing mentioned earlier is the desire to create a more stringent kind of cross-validation for these codes. So what we'll do is take a set of 6 oxides per chemical element for most of the periodic table. We'll run the equation of state for all the codes and oxides and compare them and try to understand if there's margin for improvement. Many of the codes have co-developers involved, so we're very optimistic that this collaboration will really help not only validating the accuracy of the codes, but also implementing automatic recipes for anyone to run at that level of accuracy. So the final topic I just want to touch on in the last few minutes is that of accessibility, is putting these workflows and the data they produce in the hands of users, making it as easy as possible for non-experts to analyze, reproduce, or extend our results. And the first thing we did with this is, as we were running the project, was to release everything inside with what we call Quantum Mobile. So this is essentially a virtual machine that we build and maintain, which, among other things, contains AiiDA. It contains all of the quantum codes I mentioned, the ones that have an open license. And it contains all the data plugins and workflows, including the common workflows and its command line tool. Within this, you can then just run the command that I was showing earlier, running it here with a Quantum Espresso with fast protocol, and I submit to the AiiDA daemons, and it tracks all the processes that are running. You can easily run this on your laptop or also interface with a supercomputer. Then at the end, you just run a command and it will show you the results. And since we run with AiiDA, you can automatically track all of this and have all the data provenance stored for you to inspect. And this is exactly what we use to run the tests and generate results for the paper. Then we could use AiiDA to generate data archives and publish these on our Materials Cloud online repository, together with all the scripts to reproduce it. And you can see, when you go to Materials Cloud, you can look at this data graphically, inspect it in the browser. This is actually served up by the AiiDA REST API. And you can see the different simulations that have been run and expect what their inputs were. And then building on this API, I'll also just quickly mention AiiDA Lab, which is another thing. We would like to be able to put this all into a graphical user interface, release an app based on Jupyter, and then this interface can be deployed in a scalable way for anybody to access. Okay, and with that, I'd just like to conclude. I think I've got about 10 seconds left. I just want to thank all the people that have made this possible. First of all, the AiiDA and Materials Cloud teams, all the people contributing to AiiDA and the various plugins, all the authors of the Common Workflow project, but also the new collaborators who are coming in on the next generation of Common Workflows. And I'd like to thank also the funding that made this possible, in particular NCCR Marvel in Switzerland and Max European Centre of Excellence, the Swiss Universities Fund, and a number of other European projects, Marketplace, Dome, Intersect, Big Map, and NFFA. Just to summarise, we computed it for 11 different quantum engines. It's very easy to use, but at the same time, flexible for experts and designed to be interfaced with graphical user interfaces. And we use this for a basis for verification and validation studies for the X-side set and the starting point for more common workflows. And with this, I thank you for your attention, and I'm happy to take any questions.
Okay, thank you, Chris. Are there any questions?
So firstly, this looks very cool, but can you talk about the level of difficulty involved with integrating another tool in there? Like suppose I have a quantum code that you've never heard of, and I have to do the integration because it's my code or because I'm the one who wants it. How hard is that? I mean, I know you said to reach out to you, but...
Yeah, so I mean, to add another, essentially you're adding another Python package, an AiiDA plugin. We have a cookie cutter for that, say, that you can go on. And what you do is essentially you'll just want to define this code. We hold tutorials. You're welcome to come in. I think in August we have another one. But it's you essentially create this Python package. You define a calculation plugin that says how to do this, and that's really the key basis point for it. And then you can plug that into workflows. But I'd like to think it's fairly, as long as you have a relatively good understanding of Python or reasonable understanding of Python, then you can create a Python package and you can make your plugin. And you can see, as I say, there's already 11, 15 of these plugins that you can go and have a look at.
Great, thank you.
Thank you.
Yeah, thank you. Very nice talk. I would be interested in the precision aspect. So is it dynamic for every quantity, or is it just like general settings like a certain energy cutoff and k-point mesh to be a precise calculation?
Yeah, so yeah, for the precision, it's, as you say, the energy accuracies for quantum expressors, say, the basis set selection, the number of k points, all of this trying to balance with these, I say, with this fast and precise and moderate, the level of accuracy versus how long it takes. So the idea is that it should only take a few minutes for the fast, and then for precise, it's your kind of production runs.
All right. So as a user, I would be very interested if I can say the precision on the final quantity, right? So maybe I want my bulk modules with 1% precision. And then if we can go back to see, okay, what kind of input parameters do I need to get there? Just as an idea maybe for the future of the project.
Yeah, no, thanks. That's very interesting. Yeah, I'd be happy to.
Yeah, we should definitely discuss about it.
Obviously, it's very sympathetic in what we're trying to achieve here. But yeah, for this, I mean, the idea was obviously to have this two-level system where we only have these three protocols to make it as simple as possible for users. And then if you want to try to get more precise about what you want to do and how you want to optimize your parameters, then you can, there's a hook to be able to get in there and be able to do that.
Okay, thank you.
Any other questions?
Maybe I'm asking you to just go back to slides that you presented, but can you talk a little bit more about how work or tasks are managed and the either how you approach it or what you find are best practices for using HPC resources, and where the responsibility lies for customizing for different computing environments, like how much of that does or should live in a package or in the AiiDA stack versus in the user's environment? Can you talk more about HPC?
Yeah, sure. So I guess, thanks for the question, great question. The main point of AiiDA is a present generally lives inside your local computer. So AiiDA running will live inside your local computer. The interface with the HPC, again, this is a pluggable entry point system. We have plugins to interface with the HPC, so whether it's SSH or some other kind of API. And this is how you upload and download information. And then we have plugins to interface with the scheduler of the HPC. So essentially, what we'll do is we'll generate on the, say, the client side, all of the data, the inputs to the calculation. They'll be uploaded to the HPC probably via SSH. Then again, via SSH, we'll interface with, say, Slurm scheduler and tell it to run the job in a certain, and then we'll poll that to see when it's finished, and then take the data back. Does that make sense? So the interface with most of the schedulers, available schedulers like Slurm, is all built in, and the SSH connection is all built into AiiDA core. But as I say, it's all built on a pluggable system where you can define your own. If you have a certain HPC that has a certain protocol or a certain scheduler that it needs to interface, even I know when I was doing it at Imperial, their setup for their scheduler was slightly different, and I couldn't use the built-in one, so I had to extend it. So that's where the responsibility lies. Then you can extend it with a plugin. Hopefully that answers your question.
I have a question. How many workflows besides structural relaxations can you actually standardize across so many different software?
So as I mentioned, I mean, we've started with the structural relaxation and the band structures. Now we're trying to do the density of states and the partial density of states, and then then we'll see where we can go from there. Obviously, trying to do this kind of standardization, I mean, as a first step, the point is also that these can be used as building blocks. You're always, for some kind of workflow, you can take them and customize them to your own workflows. If you have a relaxation that runs, that can be just a component that goes in then say maybe you need some extra steps for your specific code. But yeah, I think we'll get through the first ones and then build on it from there, how far we can go into doing very specific things.
All right, thank you,
Okay.
Chris, for the great talk.
Thank you.